Good day, everyone. My name is Han Ping Hui from 4SMJC. My final year project title is Effect of Particle Size on Powder Flowability under the supervision of Prof. Dr. Izzat Chan bin Abdullah. I will be presenting on the introduction, problem statement, objectives, methodology, results and discussion, as well as conclusion of my FYP. In chemical, food and pharmaceutical industries, over 70% of materials are handled in the form of relatively free-flowing powders. This is due to their easy processability, which can bring benefits for the manufacturing process and application of the products. Some examples include milk powders, cocoa powders, and spices produced by food industry, medicines in tablet form by the compression of powders in pharmaceutical industry, cosmetics, and the widespread use of catalyst powders and polymers in chemical industry. In the powder processing industry, some powder flow problems which may occur in the production line can result in production stoppage, industrial financial losses, silo failure, and sometimes even fatal accident due to grain entrapment. Thus, predicting powder flowability plays a crucial role in powder handling industry. Up until now, however, there's no standard and no universal indicator for powder flowability measurement which can be applied to all types of powder. Therefore, the objectives of this study are to analyze the change in powder packing with the effect of particle size in terms of packing density and bed voidage, to investigate the effect of particle size on powder flowability, and to study the reliability of Hosner ratio HR, Carr index CI, and angle of repose AOR in predicting the flowability and flow characteristics of powders. For the scopes of study, two types of inert powder, namely fluid cracking catalyst FCC and fire retardant filler FRF, were used as the materials in this work. The sizes of the fine and coarse powders were below 100 micron. The powder flowability was measured by Hosokawa powder tester model PTS using aerated method, which involves density and angle measurement. HR, CI, and AOR were used as the powder flowability indicators to predict the powder flow characteristics. The correlation between these three indicators was determined. The reason of selecting HR, CI, and AOR is due to their simplicity and accuracy, which meets the requirement of industry today. They can predict the powder flowability accurately and almost instantly, as it involves quick and simple procedure which can be done within around 15 minutes. In order to achieve the objectives of the project, the methodology includes powder packing and powder flowability testing methods. Hosokawa powder tester, as shown in the figure on the right, was selected as the equipment since it is capable of measuring both bulk density and angle of repose. Porous FCC powder with spherical particle shape and non-porous FRF powder with angular particle shape were selected as the materials used. For FCC powder, sieving was required to separate it into two portions, fine and coarse powders, whereas for FRF powder, sieving was not required as two sizes FRF40 and FRF5, which are already in the required size range, are available. To achieve Objective 1, powder samples with different particle sizes were prepared by adding fine powders to coarse powders in increment. The powder mixture formed contained fine powders with weight percentages of 1%, 2%, 5%, and so on. The mean particle size of each sample was then calculated. A total of 13 samples were prepared for each FCC and FRF powder. For the measurement of bulk densities and bed voidage, after setting up the instrument as shown in the video, the aerated density was measured by filling a 100 cc cylindrical cup with the powder sample through a vibrating sieve, whereas the tap density was measured by tapping the cup vertically for 180 times while adding extra powder to keep the cup full. The voidage of aerated and tapped powder beds were then calculated based on the densities obtained. To achieve Objective 2, Hosner ratio and Carr index were automatically calculated by the software of Hosokawa powder tester after measuring the bulk densities. For angle of repose measurement, the powder sample was poured through a vibrating sieve and glass funnel onto a plate to form a conical powder heap. The image of the powder heap was captured and the AOR was then calculated by the software. To achieve Objective 3, the data analysis was carried out to determine the correlation between HR, CI, and AOR as powder flowability indicators, the cut size between free-flowing and cohesive powders, and the comparison between the packing of FCC and FRF powders. As for the results and discussion, the effect of particle size on powder packing is illustrated by Figure 1, which shows the graph of tap density versus particle mean size, and Figure 2, which is a graph of voidage versus particle mean size. But voidage is the inverse of packing density. Thus, the voidage show opposite trend with tap density. As the particle mean size increases, initial increase in tap density and initial decrease in voidage are observed for both FCC and FRF powder. This can be clearly explained by the figure presented by German and Park in 2009, where the fine particle starts to fill the interstices between coarse particles. The trends continue until they reach the maximum packing density and minimum voidage, which occur at 15 micron for FCC powder and 21 micron for FRF powder. This is where the optimal powder packing is obtained, as the fine particles almost completely fill all voids between the coarse particles. Beyond 15 micron and 21 micron, the tap density starts to decline while the voidage starts to increase. This is because there are fewer fine particles available to fill the interstices between the coarse particles, thus leaving more voids in the powder bed. Based on Figure 2, the voidage of FRF powder is greater than that of FCC powder. This is because FCC consists of particles with more spherical shape compared to FRF particles with more angular shape. Hence, the fine FCC particles can roll in the voids between the larger spherical particles more easily than fine FRF particles. Therefore, it indicates that FCC powder packed better than FRF powder. To investigate the effect of particle size on powder flowability, the graph of Hosner ratio HR against particle mean size is presented in Figure 3. HR of FCC and FRF powders do not differ significantly from each other. Based on Geldet's classification, powders are categorized into Group A, C, and C with respective HR range and flowability indication. Taking FCC powder for explanation, it is observed from Figure 3 that particle mean size smaller than 25 is cohesive, greater than 38 is free-flowing, between 25 and 38 exhibits both cohesive and free-flowing behavior. As the particle mean size increases, HR decreases, indicating that the powder flowability turns from cohesive to free-flowing. This is because the presence of greater amount of coarse particles in the mixture decreases the interparticle friction and cohesive forces between the particles. Therefore, it can be established that powder flowability increases with particle size. The second indicator is Carr index CI, where the effect of particle size on powder flowability is demonstrated by Figure 4, which is the graph of CI versus particle mean size. As you can see from the graph that the larger the particle size, the lower the CI, and thus the greater the powder flowability. This trend is in accordance with the results obtained by the HR measurement, thus strengthening their reliability as flowability indicator. Based on HR and CI criteria, the cut size between free-flowing and cohesive powder ranges from 30 to 35 micron. However, the detailed classification of CI is not necessarily preferable in predicting powder flowability, as the difference between each group is not significant. As for the effect of particle size on angle of repulse AOR, the graph of AOR against particle mean size is presented in Figure 5. The fluctuation of AOR is observed for FCC powder mixture when the particle mean size is below 10 micron. The inaccurate and inconsistent AOR measurement may be the result of the formation of powder heap with irregular shape. Overall, Figure 5 illustrates the decrease in AOR when the particle mean size increases, which confirms that powder flowability increases with particle size. However, the results obtained by AOR classification differ significantly from HR and CI classification. Based on AOR criterion, the cut size ranges from 16 to 25 micron. The inaccurate results observed may be due to the difficulties in forming the conical powder heap, thus reducing the reliability of AOR as a powder flowability indicator. In order to study the reliability of HR, CI, and AOR, the comparison between the three indicators are illustrated by Figure 6, HR versus CI, Figure 7, AOR versus HR, and Figure 8, CI versus AOR. The linear relationships among them confirms that all the three indicators are capable of predicting the powder flowability in the right direction. It is observable from Figure 6 that HR criterion is in exact agreement with CI criterion, but the detailed classification of CI is not necessarily preferable. On the other hand, AOR classification is not as accurate as HR and CI classification. Therefore, it can be established that HR is the most reliable, sensitive, and accurate powder flowability indicator. To conclude, all the objectives of this research have been achieved. For powder packing testing, optimal powder packing is achieved at maximum tap density and minimum bed voidage. The more spherical shaped FCC powder packed better than the more angular shaped FRF powder. For the powder flowability testing, HR, CI, and AOR decrease when the particle mean size increases, indicating that powder flowability increases with particle size. The cut size between free-flowing and cohesive powder ranges from 30 to 35 micron. Last but not least, for powder flowability indicator study, the linear relationships among HR, CI, and AOR show that they are able to provide flowability indication in the right direction. Hosner ratio is proven to be the most reliable indicator among them. That's all for my FYP presentation. Thank you so much for watching.